everyone to the Zone 18 SPS meeting. Go Zone 18.
Yeah.
So we have people here from Chico, Bakersfield.
Yeah.
Who else?
Sac State.
Sac State.
We're those
Fresno.
guys.
Okay. Oh wait. How can I forget?
I know you would have hoped.
What now?
You would have hoped you wouldn't forget.
Okay, so before we move on to the evening's main event, I have some brief announcements to make. So seeing as how this is the SPS zone meeting, tomorrow we have a full slate of events. Okay, the planetarium show, demonstration contest, more plenary talks, tons of pizza, but also in there are going to be student talks and posters. So if you're interested in giving a student talk or you're interested in giving a poster, see Olivia, SPS president for Fresno State.
Stand up, Olivia. Don't just raise your hand. Show your face. Show your face.
See Olivia after the talk.
All right.
Okay. And I'll probably make this announcement again after the talk as well. And also there'll be social events afterwards, and so for that also see Olivia.
We're gonna make a big block.
Okay. So actually, you guys have like a bowling or like movie night or some cool stuff planned. Okay. So, without further ado, let me read Dr. Santer. Dr. Santer is our keynote speaker for this conference, and I'll read off a very impressive CV or intro. So, Dr. Ben Santer is an atmospheric scientist at Lawrence Livermore National Laboratory. His research focuses on such topics as climate model evaluation, the use of statistical methods in climate science, and identification of natural and anthropogenic fingerprints in observed climate records. Dr. Santer's early research on the climatic effects of combined changes in greenhouse gases and sulfate aerosols contributed to the historic discernible human influence conclusion of the 1995 report by the Intergovernmental Panel on Climate Change, IPCC. His recent work has attempted to identify anthropogenic fingerprints in a number of different climate variables. Okay. Dr. Santer holds a PhD in climatology from the University of East Anglia, England. So after he finished his PhD in 1987, he spent 5 years at the Max Planck Institute in Hamburg, Germany, where he worked on development and application of climate fingerprinting methods. And actually since 1992, he's been a member of Lawrence Livermore National Lab in their climate model diagnosis and intercomparison area. So Dr. Santer has won many awards. He won the U.S. Department of Energy E.O. Lawrence Award, Distinguished Scientist Fellowship from the U.S. Department of Energy, Office of Biological and Environmental Research, Fellowship of the American Geophysical Union, membership of the U.S. National Academy of Science. It says here also he recently visited the Juneau ice fields in Alaska, I guess in reference to some climate work. And actually the most impressive thing is in 2000, actually it says 1998, this is 2008, he was awarded a MacArthur Fellowship. So if you guys know, so the MacArthur Fellowship has another name, it's called a Genius Grant. So it's a big deal. Okay? So actually, without further ado, let's welcome Dr. Ben Santer.
I still have to carry out the trash at home though and pick up dog poop, so all of that stuff doesn't mean anything really. It's the friends you meet along the way. Those are the real awards and rewards in any scientific endeavor. And I'm delighted that this evening we have Tom Wigley here from the University of Adelaide in Australia. Tom was my PhD supervisor. He's one of the world experts on climate science, and if I get any inconvenient questions that I can't answer,
Always good to
yeah. This isn't just a pretty picture here. This is satellite imagery of the total amount of water vapor in Earth's atmosphere on the day Hurricane Katrina made landfall. Wow. So this little blob here, this is Katrina about to hit the Louisiana coast. And you can see here out there in the Pacific, other magenta blobs, typhoons spinning in the tropical Pacific. These these beautiful tendrils too of high concentrations of water vapor. We call them atmospheric rivers or pineapple expresses. They can have huge implications here in California when one of those hits the coast. And I use this to illustrate that this is one of the things we look at, satellite measurements of water vapor in the atmosphere to figure out whether there's some human fingerprint in this water vapor data. Has there been some increase? Can everyone hear me at the back, or would you like me to use the microphone?
Can you use the mic, please?
Sure.
Thank you.
We use these satellite data sets to determine whether there's some human fingerprint in fields like temperature, moisture, and the cool thing is that since the late 1970s, we can do this globally. So we've moved from local and regional measurements of climate to the capability to truly monitor global scale changes in things like water vapor. Well, at the start, let me declare my values. I'm not just a climate scientist, I'm a climber. I've spent the last 50 years in high alpine environments around the world. And in addition to the scientific imperative to understand the nature and causes of climate change, I firmly believe that there's also a moral and ethical imperative to preserve these and other beautiful high alpine places and many other environments for future generations. So those are part of my values, not just to understand the science, but also to figure out what kind of world we want to leave behind for future generations. And all of these are pictures I've taken. Over one human lifetime, I've witnessed profound changes in some of these places. Some of the glaciers I stood on in the Alps many, many years ago are different. These last images are from the Juneau ice field in Alaska that Doug mentioned. I've had the privilege of going there a couple of times. I'm going back again this summer. Folks have been going to the Juneau ice field since the late 1940s to measure glacial mass balance, to look at changes in Alaskan glaciers. And if you stand here, where I was when I took this picture, above Camp 10, looking down on the Taku Glacier, climate change isn't academic. It's not some theoretical thing. You see evidence of change in Alaskan glaciers everywhere you look. And in fact, the only glaciers in Alaska that are advancing are ones that are losing mass as they're advancing. They're surging. So meltwater is being channeled to the base of the glacier, and they're moving fast even as they're losing mass. And in fact, a paper came out just a little while ago that has looked using satellite radar altimetry to look at the mass of Alaskan glaciers. And on average, Alaskan glaciers have lost about 75 gigatons per year of ice since early in the 21st century. So climate change is not just some theoretical thing of concern to a few scientists somewhere. As Doug mentioned, both Tom and I have been involved with the Intergovernmental Panel on Climate Change, or IPCC, since its inception in the late 1980s. And the role of this organization is to advise the governments of the world what we know about the causes of climate change, the physical climate system, what we know about likely impacts of climate change on things we care about, and mitigation and adaptation strategies. And Tom and I were both lead authors on the detection and attribution chapter, which dealt with causes of the second assessment report in 1995. And after several years of study, lots of meetings all around the world, many dozens of scientists participating in this evaluation of the then available scientific information, our bottom line finding was, quote, "The balance of evidence suggests a discernible human influence on global climate." And both of us, Tom and I, spent roughly 1.5 years of our scientific career defending that finding and the process by which it had been reached after publication of the report. And it's kind of sobering when you think about it that no matter what you do for the rest of your career, you will be inextricably linked with that one sentence for the rest of your life. So if one sentence defined you, what would that one sentence be? Do you know it yet? Is it still to come? Anyway, in our case, in my case, certainly that one sentence will follow me to the grave. Well, the cool thing is that back then, that cautious balance of evidence finding was controversial. It generated some pretty healthy ripples in the ponds of science and politics. Of course, extraordinary claims do demand extraordinary proof. An independent group of scientists in 2001 reevaluated the evidence 6 years on. They came to a much stronger conclusion regarding the reality of human effects on climate. Unlike us, they tried to quantify the size of the human effect on climate. And in 2007, in the fourth assessment report, they came to a stronger statement than the third assessment report. They use this likelihood language. Most of the observed increase in globally average temperatures since the mid-20th century is very likely due to the observed increase in anthropogenic greenhouse gas concentrations, where very likely had a specific probabilistic meaning, greater than 90% confidence that that statement was correct. And the most recent report in October 2013 went even further still. It used extremely likely, greater than 95% probability this statement was correct. And unlike earlier work, it looked beyond temperature. So it said, we see fingerprints of human activity not only in surface temperature, but in snow and ice, in the water cycle. So my job today, as I see it, is to give you some sense of what is the scientific underpinning of these findings. How did we get from the balance of evidence to extremely likely that we see human fingerprints in many, many different attributes of the climate system? So this is what we're going to talk about. First of all, I'm going to tell you a little bit about the drivers, both natural and human, of changes in climate. Then we're going to talk a little bit about the observations of climate change. There's this narrative out there that our observational understanding of climate change rests on one or two killer data sets, like surface thermometer measurements. And if you take those one or two killer data sets away, it's a house of cards. Everything collapses. That's not true. And of course, we've now for many decades looked at a variety of different aspects of the climate system, and that's what gives us confidence in the reality of warming. You're not just looking at temperature, as I'll try and convince you. Then I'll tell you a little bit about how do you put it together. So how do you, given some understanding of the factors that influence climate, and giving observations, and given computer models of the climate system, how do we look at cause and effect relationships? How do we figure out causation? And finally, I'm going to get into some of the projections for future changes in temperature and in sea level. What might the climatic shape of things to come look like for the 21st century? And hopefully there'll be plenty of time for questions, because that's part of the reason that we are here to be accountable. I firmly believe that if you're funded by the federal government to do this kind of work, you have a responsibility to be accountable, to answer questions that people have about what you did, what you learned, and why it matters to them. So that's one of the reasons I'm here tonight. Okay, so one take-home message is climate change is not an either-or proposition. It's often portrayed as all natural or human. It's not. It's both, clearly. We know that there have been changes in both natural and human drivers of climate. Let's look at the natural ones first. So one is changes in the sun's energy output. We know that the sun is a variable star. Its energy output varies on timescales of 11 years and longer. Since the late 1970s, as I'll show you later, people have made direct measurements from space using a variety of different satellite-borne instruments of the sun's energy output. Further back in time, before the 70s, people look at things like cosmogenic isotopes, like 10 beryllium, isotopes whose abundance is related to changes in solar activity. They also look at things like sunspots and make inferences about changes in the sun's energy output on timescales of the last 4 or 5 centuries that we have sunspot records. So there are a variety of methods of going back further in time and trying to reconstruct changes in the sun's energy output. In addition to changes in the sun, there are very large volcanic eruptions. What you see here is satellite imagery of the eruption of Mount Pinatubo in the Philippines in June 1991. When you have a very large volcanic eruption, it produces sulfur dioxide. If that sulfur dioxide makes it into the upper atmosphere, the stratosphere, it can form liquid phase sulfuric acid droplets. And those droplets reflect some portion of incoming sunlight back to space, prevent it from penetrating deeper into the atmosphere. And the effect of a very large volcanic eruption is to cool, sometimes for years at a time. So we'll be looking at some of those volcanic eruptions a little later in this talk. In addition to changes in the sun and volcanic material in the atmosphere, there are these natural cycles, things like El Niños and La Niñas. So what you see here is satellite imagery of one of the largest El Niño events in the 20th century, the 97-98 El Niño on the left-hand side. Those white colors, that's warming, very large warming of the eastern equatorial Pacific. So, you know, think of El Niño and La Niña as a kind of internal oscillation of the climate system, a mode by which the climate system likes to ring naturally. And there are many of these things. There's a whole zoo of these oscillations. El Niño, La Niña, that's one. There are oscillations in the Atlantic, in the North Atlantic, in the Southern Ocean, all kinds of different things that operate in different areas on different time scales, and they have nothing to do with changes in the sun, volcanoes, human influence, purely internal oscillatory modes of the climate system. So all of this stuff, changes in the sun, changes in volcanic aerosols, these internal oscillations, taken together, that's the rich year to year and decade to decade and century to century natural noise of the climate system. And that's the noise against which we're trying to identify some human effect on climate. So, what do those human influences look like? Here you see 2,000 years of changes in 3 powerful greenhouse gases, carbon dioxide, methane, and nitrous oxide. So the carbon dioxide in red, we have direct measurements of that since the late 1950s. Before that, going further back in time, people have made clever inferences about changes in atmospheric levels of CO2 by looking at ice cores primarily. And now with ice core records in Antarctica, we can go back 800,000 years, probably a million years, as I'll show you later. Beautiful, beautiful detective work. Now, if you look at the red line, there's been an increase from the time of the Industrial Revolution, about 280 parts per million CO2, to the historic threshold of over 400 parts per million now. And we know by looking at lighter and heavier isotopes of carbon that 75 to 80% of that increase in CO2 is us. It's fossil fuel burning. That's not a belief system. That's not really something that's controversial in the scientific world. We know the causes of most of these increases, and the causes are not natural. They're human. In addition to changes in levels of these heat-trapping greenhouse gases in the atmosphere, there's also particulate pollution. So this is satellite imagery of smoke and haze from biomass burning in Guatemala and Mexico in 1998. We know that there are a whole bunch of different activities that produce particulates in the atmosphere. Some darker soot particulates absorb incoming sunlight and heat the atmosphere. Others, like these sulfate aerosols that Doug mentioned earlier, actually reflect incoming solar radiation and cool locally. And where you have high burdens of these particulates in the atmosphere, you have the potential to affect local and even regional climate. Again, not natural. In addition to changes in greenhouse gases and particulate pollution, humans have transformed the surface of the planet. So that final panel there, that satellite imagery of logging roads in Rondônia in the Brazilian rainforest. So we can see these kind of perturbations from space. And when you change the reflectivity of the Earth's surface in that way, when you change the fluxes of moisture from the soil into the atmosphere, again, you have the potential to affect both local and regional climate. So this is human. The previous slide was natural. And the real challenge is all of this stuff is going on simultaneously. It's not an either or. In the real world, all of these factors are operating to a greater or lesser degree simultaneously. And that's the challenge, doing that separation of the natural from the human sequence.
Yeah.
Cool. And we have them at Livermore too. I remember on the occasion of the lab's 50th anniversary, they were going to get Arthur C. Clarke from Sri Lanka to appear on this video feed live, and it was very embarrassing. They couldn't get it to work. Here is the 50th birthday of Lawrence Livermore National Lab, and they couldn't get the technology to work. So you shouldn't feel bad. So this is it. This is ice core data, I believe, from Antarctica and Greenland, from a bunch of different ice cores. And this is some reconstruction of the last 800,000 years of the history of atmospheric CO2. And you can see these nice ice age cycles there, and that for much of the last 800,000 years, atmospheric levels of CO2 have fluctuated between about 180 to 280 parts per million. And now we're past this historic threshold of 400 parts per million. And the point of this slide is that we are, at least over the last million years, in uncharted territory, and we have some control based on the decisions that we collectively reach in the next couple of decades in particular about how we choose to use energy and how much and what we choose to use to influence the landing point. You know, do we go to the green world of over 550 parts per million CO2? Or do we go to the yellow world of nearly 900 parts per million CO2? And those choices that we make, in a very real sense, will influence the outcome over the next century and far beyond. All right, observations. So this is information from the 5th assessment report, the 2013 report of the Intergovernmental Panel on Climate Change. And what you see in the top panel is our best shot, our best estimate of the average temperature of the planet from millions of observations of land surface temperature, ocean temperature measurements. This is the kind of work that Tom led when he was the director of the Climatic Research Unit in the UK. There are three lines there, three colored lines in the top panel. Those are from different groups. One is from the Climatic Research Unit at Hadley Center in the UK, and there are two US groups, one in New York, one in Asheville in North Carolina. And different groups look at the same raw data in different ways. They have to adjust for changes in instrumentation, changes in sampling as a function of time, inhomogeneities, urban warming effects, as a city grows up around a site where you're monitoring temperature. So there are all sorts of, in any observational data set construction, there are all sorts of subjective judgments you have to make. It's very reassuring that three groups do it independently and more or less get the same global mean result. And that result is that we've seen about 1.5 degrees Fahrenheit warming since the Industrial Revolution. So that's our best shot. And if you look at things in the bottom panel, those are 10-year averages. And again, three colored lines for different observational groups that have done this. The gray bars give you some sense of the uncertainty. And the bottom line finding of the 5th assessment report, one finding was that in the Northern Hemisphere, the last 30 years were likely the warmest 30-year period in the last 1,400 years. So this is what it looks like spatially then, or geographically, if you take that global mean that I just showed you and look at what that looks like at many locations on the Earth's surface. Virtually everywhere has warmed, except a little blue blob there in the North Atlantic. And the warming, for well understood physical reasons, tends to be larger over land than over ocean. So this is our best estimate of what's actually happened, and again, virtually every location on the Earth's surface has warmed, if you take the long view. Now, as I mentioned, various folks have said, well, we don't trust surface measurements, and if you take those measurements away, then there's no evidence of warming. That's not true. As I said earlier, people routinely look at a bunch of different things like northern hemisphere snow cover, Antarctic and Arctic sea ice extent, changes in the uppermost 700 meters of the ocean in ocean heat content, global mean sea level, and in each case, a different color there means a different group has done the analysis. So that's another thing that gives you some confidence in the reality of the result, that different groups using different methods and starting from slightly different raw data independently go through this complex process of trying to come up with global scale changes in ice and sea level, in ocean temperature. And all of this is physically consistent with the surface temperature data that I just showed you, with a warming planet, which is what led the IPCC to conclude in the 2007 report that warming is unequivocal. And when you get a bunch of scientists, cautious, conservative scientists from many, many different countries, agreeing that warming is unequivocal, that's a pretty strong statement. Okay. All right. We learned a little bit about the drivers, a little bit about the observation. How do you put it all together? This is a very famous figure from the 2007 report of the IPCC. And what it shows you there in black is a smooth version of the global mean surface temperature data I showed you earlier. And it shows this sort of rapid warming over the first half of the 20th century, some cessation of warming from about 1940 to 1970, and more rapid warming recently. And then you see two envelopes, a pink envelope and a blue envelope. So those are from model simulations, with back then probably several dozen different computer models of the climate system developed at a number of countries around the world. So you're physicists, and Einstein was fond of Gedankenexperimente, thought experiments. So experiments you could do in your brain, but you couldn't do in the real world. Computer models of the climate system are the ultimate Gedankenexperiment. So you can do the control. What might the climate look like without any human intervention, without any human-caused changes in greenhouse gases? That's the blue envelope. So the blue envelope is when you run climate models just with estimated changes in the sun's energy output and in volcanic aerosol loadings, according to our best understanding of how those things actually changed over the 20th century. What do you see? So in Blue World, in World Without Us, you don't capture the warming in the second half of the 20th century. In Red World, where you run exactly the same models with both these natural factors and human-caused changes in greenhouse gases, particulate pollution, to first order, you do capture that warming. Now, this isn't compelling statistical evidence by any stretch of the imagination. We'll get to that in a minute. But what it does show is the power that with the simulations, you can do the controlled experimentation that we can't do in the real world. In the real world, we have one planet, one atmosphere, where all this stuff, natural and human, is happening simultaneously. In the model world, you can change one thing at a time. And that gives you a lot of understanding of the expected climate changes in response to individual factors, like the sun, like volcanoes, like greenhouse gases. So let's take a look at that. So, one of the claims that people have made and continue to make is it's all the sun. So all of this that you see here, all of the estimated surface warming for the last 120, 130 years is due to an uptick in the sun's energy output. So again, these are observations of land, ocean, and combined land and ocean surface temperature. They show this profound warming, and folks continue to argue that all of this is due to an uptick in the sun. Now, one thing I would say is that we routinely consider whether such hypotheses fit the bill. Could indeed some uptick in the sun explain the observations? Let's look at that. So, cartoon time here. Here's the sun, here's the Earth's atmosphere in cartoon form. Imagine there's some uptick in the sun's energy output over the 20th century, and you get essentially more solar radiation arriving at the top of the atmosphere and heating throughout the full vertical extent of the atmosphere. Now, you can look at this in model world too. You can do simulations where you just change the sun, and that's what you get. You get heating from the top of the atmosphere right down to the surface. So, how does the real world atmosphere actually behave? What does it look like? And what you see here is a slice through the atmosphere. We're looking from the South Pole on the left to the North Pole, and from the surface right up into the stratosphere. These are beautiful measurements from so-called microwave sounders. These are instruments carried on polar orbiting satellites since the late 1970s. They measure the microwave emissions of oxygen molecules. And because oxygen is fairly homogeneously distributed in the atmosphere, those microwave emissions are proportional to the temperature of broad layers of the atmosphere. And by measuring at different microwave frequencies, you can back out the temperature of the lower stratosphere, the mid to upper troposphere, and the lower troposphere. And one of the premier groups involved in that satellite microwave remote sensing is right here in California, Remote Sensing Systems in Santa Rosa. They're the best. And this is what their data show. They show cooling of the upper atmosphere, with largest cooling over the Antarctic ozone hole, and warming of the lower troposphere, with largest warming over the Arctic, where we've seen the largest retreat of Arctic sea ice over the last 2 to 3 decades in particular. So the observations that we've made from space are fundamentally inconsistent with the sun explains everything hypothesis. The next time someone tells you it's all the sun, ask them, why is the upper atmosphere cooling if it's all the sun? Why? That is really an inconvenient piece of information that's, okay, short digression here. Another knock on climate models is they're not falsifiable. They can't make predictions that we can actually falsify with real world data. Not true. So back in the 1960s, some of the first scientists, say in Princeton, in Boulder, where Tom was, in the UK, were performing simulations where they doubled pre-industrial atmospheric CO2 levels, and they saw this same curious pattern, warming low down and cooling higher up in the atmosphere, because when you increase CO2, you more effectively trap heat lower in the atmosphere, and to restore energy balance, the upper atmosphere has to cool. And actually, you get the largest cooling right at in the middle to the upper stratosphere at about 40 to 50 kilometers above the Earth's surface. Now, back then in the 60s, we didn't have the satellite data. We really didn't have the weather balloon data either, because weather balloons burst when you got them above about 20, 25 kilometers. So we didn't know whether there was actually cooling at higher levels in the atmosphere. Those early pioneering calculations could have been wrong, but they weren't. Subsequently, weather balloon satellites have confirmed this warming of the lower atmosphere and cooling of the upper atmosphere. And when you run model simulations with combined changes in greenhouse gases, particulate pollution, stratospheric ozone, there are some differences there between the simulations. Those are results from about 28 climate models with human effects. But to first order, you see this same warming low down, cooling up high. And that is fundamentally inconsistent with the sun, with natural cycles, with volcanoes, or with some combination of the sun, volcanoes, and natural cycles. So there in red, you see the information I mentioned earlier. Those are the satellite measurements of the sun's energy output from a variety of different instruments. You see the nice 11-year solar cycle there, the difference between solar max and solar min.
The kicker is that over the period we've actually monitored the sun's energy output from space, there's been no overall increase in the sun's energy output. But over the same time, global mean temperature has increased. So again, that's a fundamental problem that you have to overcome if you posit that the sun explains all warming. Well, that doesn't work very well over this period here. It certainly doesn't work in terms of the stratospheric cooling. So the message from this kind of work is, look at all the data. You can't just look at one tiny segment of the data. You have to look at everything. And this sort of fingerprinting work has been done not only with atmospheric temperature, with the height of the tropopause, the boundary between the lower atmosphere and the stratosphere. It's been done with ocean warming. What you see here are sections through the major basins in the world oceans that show the penetration of a warming signal into the ocean. It's been done with things like water vapor, where Tom and I and our colleagues looked at the moistening of the atmosphere that's consistent with basic moist thermodynamics. You increase CO2, you warm the lower atmosphere and the surface, then for every 1 degree Celsius increase in surface and lower atmospheric temperature, you get about a 7% increase in water vapor. And that's exactly what we see. All right, getting towards the end here, all the fingerprinting work that I showed you relies on computer models of the climate system. And over my scientific career, we've seen this paradigm shift. 20 years ago, when Tom and I were doing this kind of fingerprinting work, it was done in the context of 1 or 2 individual climate models. You'd work with the guys in Hamburg or the folks at NCAR. Now, you can, in your office, interrogate the entire world collection of climate models. From France, from Germany, from India, from Japan, from China, from the United States. And you can look at these kind of fingerprinting issues, the pattern of response to human factors, natural climate variability, in the context of all the world's climate models. And you can do this in your office. All the simulation output is freely available to anyone, anywhere in the world. But this raises questions then, when you're not doing this kind of work with 1 or 2 individual models, but with dozens of models, is it a democracy? Should you pay equal attention to the results from Model A, Model B, Model C, or are some models better than others? Okay, so let's look at that. And can you, in some Letterman type sense, identify the top 10 climate models? And how might you do that in a scientifically justifiable way? So in 2007, Tom and I and a bunch of other people looked at that first slide that I showed you, looked at water vapor data from satellites, beautiful measurements from the Special Sensing Microwave Imager. So this looks directly at the microwave emissions from the hydrogen line, and very nice measurement of the total amount of water vapor in the atmospheric column. And we claimed that we could identify some human-caused fingerprint in these satellite records of atmospheric water vapor. And that fingerprint was primarily due to human-caused increases in greenhouse gases. And this work was criticized, quite rightly, I believe, because we had not attempted to weight the models. We had used all models equally. It was a democracy. 1 model, 1 vote. And we had used about 20 different climate models. And what you see here are the individual models. They're the colored dots. The x-axis there is the variability of water data, water vapor on 2-year time scales. And the y-axis is the variability of water vapor on month-to-month time scales. And you can see that there's a big range there of model performance. And the crosshairs are on the satellite observations, okay, from our friends at Remote Sensing Systems. So the argument went like this. Instead of using all of those models, use the ones that are closest to the observations. Use the ones in that ellipse there, and then repeat your fingerprint study and see whether you still can identify some human fingerprint on water vapor, okay? So we did that. And a couple of years later, we published a paper that tried to fold model quality into fingerprinting and tried to do this selection of the top 10 climate models. And we did that selection process in 70 different ways, using a whole bunch of different measures of model performance. And it didn't make much difference to our original results. And now I'm going to try and explain to you why that was. So here what you see is an attempt to rank these roughly 20 models from all around the world, and the identities of these models have been skillfully disguised by using national flags here. And we ranked in two different ways here. We ranked parametrically, that's what you see on the x-axis, and non-parametrically. And these particular ranks that you see here were based on 20 different measures of how well the models captured the mean state and the seasonal cycle for water vapor and temperature. So we got observations, we can compare with the models, and we can see how well each one of those models did in these 20 different measures of mean, climate, and the seasonal cycle. And focus on the gray box. So the gray box shows you the top 10 with these different ranking, the parametric ranking and the non-parametric ranking. Now, on the right, this was tougher. This was asking how well do these models capture complex patterns of variability, the changes in water vapor due to things like El Nino and La Nina, oscillations in the Atlantic. And again, look what's going to happen here. We're gonna follow through the top 4 models. And it turns out that those top 4 models are from the United States, Germany, Japan, and the UK. And you can see that the top 4 models that you selected and how well they got average climate and the seasonal cycle are not in the top 10 anymore when you look at these measures of variability. So the message from this is it's really tough to identify one metric to rule them all in a Lord of the Rings kind of sense, Model errors are very complex in space and time and as a function of variable, so there's no one model that does everything best. So we did this selection of the top 10 models in 144 different ways. And basically, what we found was that when you looked at the top 10 based on mean state metrics, that's what you see here. We looked at the top 10, we looked at the bottom 10, we looked at the variability metrics, 50 different measures of model performance, top 10, bottom 10, wow. And all 70 metrics, and the patterns are really similar. Yeah. So what's going on here? It's because the simple physics is shining through. Moist thermodynamics. So you increase greenhouse gases, you start warming up the ocean, and the warmest areas of the ocean have the largest water vapor increases. But basically the ocean is warming everywhere, and that's why the sign of the change is positive everywhere. You're getting water vapor increases everywhere. Now, when you look at the patterns of natural variability in the top 10 and bottom 10 models, again, selected a whole bunch of different ways, you can see this curious horseshoe-like tongue. So when you have an El Nino and you get this heating in the eastern equatorial Pacific, you get water vapor increases, but outside that region, you get changes of the opposite sign. So the dominant patterns of natural variability look nothing like the water vapor response to greenhouse gas increases. And that's why it didn't matter how we selected the top 10 models, because it was that basic physics that was shining through, this fundamental difference between the pattern of response to greenhouse gas increases and the much smaller scale and opposite sign patterns of natural climate variability. So this is what you need to do, not just look at one model, not just look at one observational data set, but really look at a whole bunch of different models and observations and see whether something you care about, ability to detect a human fingerprint, is sensitive to the processing choices you make and which models you use and how you select them too. And tremendous problems there for people interested in doing this kind of work. We're at the infancy of this kind of work, I would argue. A lot of interesting work left to do there because we're now in this brave new world where for the satellite observations, we have ensembles of observations where groups play through different data set construction choices and generate a whole family of observational results. And we've got to compare that distribution of observations with a distribution of model results. How do you do that? Okay, getting to the end, areas of concern. I'm only really going to talk, I think, about temperature and sea level here, but there are a lot of other areas of concern that maybe we could get to in Q&A. And I'm assuming most of you have heard about concerns regarding ocean acidification. So these are results from the 5th assessment report of the IPCC. Again, what you're seeing here are projected changes, no observations on this, in global mean surface temperature. And we have these two things, I call them red world and blue world. So these are the projected changes from roughly 3 dozen models out to 2100 under 2 different storylines, 2 different assumptions regarding population growth, technological development. The blue world, I like to call enlightened humanity, has global annual greenhouse gas emissions which peak between 2010 and 2020 and decline thereafter. And in blue world, you get an estimated global mean temperature increase from roughly 0.5 to 3 degrees Fahrenheit by 2100. In red world, business as usual, it's assumed that global annual greenhouse gas emissions increase throughout the 21st century, and you get a projected temperature increase ranging from 4.5 Fahrenheit to 8.5 Fahrenheit. So which pill are we going to take? The red pill or the blue pill? This is the same thing, blue world and red world, for global mean sea level. And in red world, the projected sea level increase out to 2100 is from 20 inches to over 3 feet. And in blue world, it's still at the upper end, over 20 inches. And I would argue that these projections are relatively conservative because for successive IPCC reports, it's been difficult to estimate and characterize the contribution to sea level rise from land ice sheets and you know, the contribution to sea level rise from thermal expansion, from the warming of the oceans, is much better understood. So it's entirely possible that these estimates are erring on the conservative side and not alarmist, as the IPCC is often accused of being. Okay, conclusions here. First message, climate change, I hope I've convinced you, is not an either-or proposition. Anyone who tells you it's all one, it's all the other, is wrong and reduces the complexities of the climate system to, you know, to this incorrect either-or proposition. The real scientific challenge has always been to figure out how much is human, how much is natural. We know beyond a shadow of a doubt that human-caused burning of fossil fuels has changed the levels of heat-trapping greenhouse gases in the atmosphere. That's not a belief system. That's not supposition. We know that for a fact. We know that warming is unambiguous. We see evidence of warming everywhere we look, in glaciers, in sea level, in the oceans, in the land, in the atmosphere. And we know from doing this fingerprinting work that when we compare complex patterns of climate change in models and observations, natural causes alone don't cut it. They can't explain the changes that we've actually observed. We know that the decisions we reach over the next several decades in terms of how we use energy and what the mix of energy-producing technologies we deploy is, those decisions will ripple down through the 21st century and beyond. They will have far-field effects in time. So we need to get it right. You know, unfortunately, we don't have the luxury of control world, and we only have one planet here. You know, much of what I presented to you today has been described by powerful folks as a scam, a hoax, a conspiracy. It's not. I wish we were wrong on the science. It'd be great to be wrong on this one. It'd be great to know that we were not leaving a world behind for future generations with rapidly changing climate. But if we're even in the ballpark with our understanding of the science, this is a serious problem. We need to devote serious attention to it. I firmly believe that collectively as a nation and as a planet, if we embrace ignorance with open arms, we all lose. You know, we got to take decisions based on the best available scientific information, which is why I'm so encouraged that all of you are here tonight, that all of you are thinking at least about careers in physics, careers that enable you to use the tools that you're being equipped with to understand these kind of problems. That's what we need. Just finally, I'm going to leave you with this image here. This is not a montage. So this Japanese artist, Azuma Makoto, attached a bonsai tree to this frame, sent it into the upper atmosphere with a balloon, and somehow managed to photograph it as well. And to me, this captures the beauty and the complexity of the atmosphere. When you see this, you recognize the fragility of life, the fragility of the atmosphere, and indeed the fact that we don't have a control room. We only have one Earth, and we've got to get it right. So thank you very much, Doug. Thanks, ladies and gentlemen, for inviting me here. My first, but hopefully not my last visit to Fresno. And I'd be happy to answer any questions you might have. And the really difficult ones, I'm going to defer to Tom.
Ben, I'll let you pick the questions.
Yes, sir.
So rather than change behavior, some have suggested we hack the climate. And could you comment on some of those schemes that people have come up with, and whether we even know enough to say if those would work or make things worse?
Well, I'm going to defer right away because it actually turns out that Tom has done a lot of work on geoengineering and is perhaps one of the most knowledgeable folks on the planet about geoengineering interventions. So Tom, if you don't mind, would you come up here and answer that gentleman's question?
Can I refuse that? It's like a lot there. Thank you.
Well, it's true. It's you do know much more about geoengineering than
Well, doesn't matter whether that's true or not, but I can I can attempt to answer the question. Some people have suggested that the way to solve the problem is to either, by artificial means, reduce incoming solar radiation, which would have a cooling effect to offset the effect of increasing greenhouse gases, by putting, say, sulfate aerosols in the upper atmosphere, or to use some method to suck CO2 out of the atmosphere artificially and thereby solve the ocean acidification problem and the climate problem at the same time, or perhaps do both of these things. And various analyses have been performed to estimate the cost of doing those things, and it's relatively inexpensive, to the tune that someone like Bill Gates could probably do these sort of things just with his own pocket money. But solving the problem by more conventional means is going to cost a tremendous amount of money. So do we have the right as human beings to tamper with a system that we don't fully understand? So there are a lot of ethical reasons why we shouldn't take the geoengineering route, but from an economic point of view, it is rather attractive. Right now, one of the arguments against geoengineering is that might mean that we consider only that solution in the absence of other methods for reducing the magnitude of future climate change. And there's a kind of ethical dilemma there that by taking a particular pathway, we might avoid the more conventional pathway. So one of the work that I've done is to consider aspects where at a certain point in the future we decide that using a conventional reduce emissions of greenhouse gases approach is just not working rapidly enough to avoid moving into an area where we've interfered dangerously or potentially interfered dangerously with the climate system, and that we might therefore have to use geoengineering in addition to the normal mitigation approach. And more likely, real world is not where we just abandon mitigation and use geoengineering alone, but where we, in a sense of desperation, employ some form of geoengineering in addition to the conventional approach. And I think that is still a real possibility. So it really depends on how successful we are politically and technologically in reducing the emissions of greenhouse gases. But if all else fails, then I think that we might have to seriously consider geoengineering. So scientists, a number of scientists have been looking at the implications of geoengineering. But the real problem is that, we don't understand what we're doing well enough now to interfere, deliberately with the climate system. So, from that point of view, we should consider the science, the possibilities in the future, but clearly we shouldn't really do anything. But, it's a complex issue. There are different opinions, and, I try to stay in the middle ground and say, well, as a last measure, we've got to consider it, we've got to understand the implications of geoengineering, we've got to do the science. Maybe at some point in the future we might have to try a little bit of geoengineering as a kind of big experiment and see, whether we really understand that possibility reasonably well enough to be able to do it on a larger scale. But that's a real, almost a signal to noise ratio. If we do a little bit of geoengineering, we've got natural variability going on. So how do we detect the the consequences of a small geoengineering experiment? So there's a lot of very interesting science that should be done and is being done, but right now it's not something we should consider as a real possibility.
Yes. Thank you, Tom.
Along that line, there seemed to be a natural oscillation between heating and cooling without our help. And do we understand what the mechanism is for the cooling that naturally happens? And because I'm wondering if we don't understand that and it goes into a correction anyway, and we give it a push for cooling, couldn't we easily put it out of, into more of an ice age kind of situation? I mean, with too much cooling?
No, that's pretty unlikely, actually. We do understand much of this zoo of internal oscillations. So we understand the time scales of some of these things. We understand a lot about the spatial patterns of some of these things. One of the problems, though, is that they're not happening in isolation. So El Nino and La Nina is happening, and there are other oscillations that are happening at the same time. And one of the things that we don't understand very well is those interaction terms. Like El Nino isn't saying, oh, geez, there's an Atlantic multi-decadal oscillation going on. I'm not going there. That's not the way that the real world works. So it's really kind of interesting and an interesting ground scientifically to understand those interaction terms between individual modes of variability. And there have been folks who proposed using information theory techniques to do that. It's a fertile ground for folks wanting to understand collectively how these things influence cooling and warming. So individually, we do have a pretty good understanding the interaction terms and the collective behavior of these modes, and how, since they're operating in different regions and on different timescales, how they interfere with each other or reinforce each other. A lot of interesting work left to be done there. Our best understanding, though, is that, correct me if I'm wrong here, Tom, without huge geoengineering, there's no danger of cooling too much and pushing ourselves into into an ice age. I think that's very, very unlikely.
But if you try really hard.
Well, there's a paper, for example, in Nature Climate Change by Peter Clark et al. That looks at how likely it is that we'll transition to an ice age given the warming that we're currently embarking on. And Peter looks at that for different emission scenarios going into the future. And the bottom line message is, it's very, very unlikely that we're going to do anything that would precipitate or hasten an ice age. And indeed, there's some evidence that it's kind of unlikely, given present rates of warming, that we'll even get to ice age conditions.
Right.
Don't be shy. You have two captive climate scientists here. Yes, sir. You didn't get to answer a question earlier, so you should ask that question or a different one now.
It was more along the lines of a comment regarding the language that's actually used in presenting these results. I'm assuming that a lot of these things are not only being presented to scientists, but also people that are in a position to start enacting policies so that we can actually start trying to move into renewable energy resources, to try to reduce the fingerprint. Scientists I've always found to be rather strange creatures in the sense that we use everyday language in a very, very technical sense. And there's oftentimes the possibility when we present these results to people that are not scientists that there's going to be a misunderstanding as to how severe some of these things happen to be. So even at the beginning of the talk, you ended up using the word or the wording likely and extremely likely to mean a 95% confidence level and then a 99% confidence level. Whereas using those terms and saying that to scientists, we know exactly what is meant. But you present that to a politician and there is the possibility that they're not really going to understand the severity of the situation. So here, it's again, my question is, how is it that you're actually presenting these things to really show off how consistent these measurements have actually been, regardless as to what country is actually doing the measurements?
Well, great question, and you're right, it's a tough job. As scientists, we think probabilistically, but most politicians want black or white, right? They don't think in terms of shades of gray. So it's a real challenge. I mean, we can't retrospectively go back in time and re-instrument the Earth and have perfect understanding of natural climate variability and its patterns and its amplitude. There will always be some irreducible uncertainty in estimating the relative sizes of human and natural influences on climate, say, over the last 120 years or so. So how do you convey the fact that as scientists, we have a responsibility to preserve that uncertainty and characterize it and quantify it, but in the political arena, people said, at the time of the balance of evidence report, well, if it's uncertain, then we don't understand everything. Come back in 20 years when you understand everything and talk to me then. And if you wait for perfect certainty, you're never going to have it. You'll be like, those characters in Waiting for Godot, waiting for something that never happens. So that's the challenge, and it really is a challenge in communicating, telling people, we know a lot about the physics, we know a lot about likely outcomes, we know a lot about risks, and in all endeavors of our lives, we're acting not in the face of perfect knowledge, but in the face of uncertainty. Medical decisions, financial decisions, climate decisions. So that's the challenge, the communication challenge. Preserving the guts, the essence, the integrity of the science, but getting across the message, hey, this is a serious problem. The likely outcomes are really, really concerning and will be for generations to come. So we need to take decisions that are risk-based decisions, not based on certainties, but based on things that will, in some sense, always be uncertain. And that's challenging, but I would say the one promising note there is that, 20 years ago, there were little incentives as a scientist for speaking about these kind of issues, or for speaking about the science you do. Fundamentally different ballgame now. Organizations like NSF, when they fund science, some fraction of your grant money is for communication of your results, what you learned. Organizations like the American Geophysical Union, American Meteorological Society, are incentivizing communication, actually giving awards for it. Google climate science fellows, all sorts of innovative ways of encouraging young scientists in particular to communicate about what they do, to get across, like I tried to at the beginning, that we're not just shallow, one-dimensional cardboard cutouts, but we're human beings and have passions and other interests in our lives, and how we do that better. It's a constant learning process. Every one of these things, like tonight, you learn. You try and do better the next time. Yes, sir.
I'm just curious. You've been in the climate business for quite some time. And I just saw a documentary called Merchants of Doubt, and another reading some articles about Michael Mann. And here are some climate scientists that have been actively kind of defamed, or there's attacks on their character because of what they're being outspoken. Have you had any kind of run-ins with folks kind of attacking you in this kind of political ideology? Does that actually tarnish or come at you and you have to fend it off?
Yes.
Many billions.
If you read the book Merchants of Doubt, then it actually starts with some of my own experiences there that I've encountered. And I have a small bit role in the movie Merchants of Doubt. And nasty stuff has happened and continues to happen. But my personal perspective is that I'm not a victim. People often try and define you by the bad things that have happened to you. To me, doing this kind of stuff is extraordinary privilege. I get to come into my office every day and learn something about this incredibly strange and beautiful world in which we live. I get to interact with, with brilliant women and men all around the world. That's privilege. I don't see myself as some victim of bad guys. When I look back on the nearly 30 years of my scientific career, the overwhelming sense is of privilege and gratitude and the good stuff that has happened to me, not the bad guys who try and make your life difficult. The late Steve Schneider, a famous climate scientist at Stanford, once said to me, Ben, you define yourself by the quality and number of the enemies you accumulate over your lifetime. And there's some truth in that. If you do stuff that's important, people care about it, and some of them won't like you and won't like what you're doing. And I think it was Earl Warren who said it best in a quote attributed to him: everything in my life I've done that's worthwhile, I caught hell for. And I fully expect to continue to catch hell for the rest of my scientific career.
So hazards weren't the job?
Sorry?
Hazards just part of the job?
It's part of doing climate science in the 21st century, that people really care about the outcomes of the science, about what you're finding. You publish something, it's like whack-a-mole. There are all kinds of people who are trying to beat you down, and what, as I see it, your responsibility is to take the scientific criticism and separate it from the nonsense, the non-scientific criticism, and respond to the scientific criticism. And I tried to show you one example of that with the water vapor thing. Hey, it was right. What some models are better than others, so does it make a difference to your results? We looked at that. Could the sun explain everything? We looked at that. And that's the challenge, to do the science necessary to address the justifiable criticism.
What about the ice cap evidence? How compelling is that evidence? I mean, here we've got this beautiful cycle going on for a lot of years, right? Do we have any type of data that goes back that many years other than that? Or?
You mean the ice core records from Antarctica and
Yeah,
Greenland?
you're talking 800,000 years, I mean, that's incredible.
Yeah, well, people have, from ice core records, tried to back out all kinds of information from looking at isotopes. They tried to back out temperature. We have some information about sea level, atmospheric composition. Beautiful, beautiful detective work by groups around the world. People are trying to look at things like volcanic eruptions as you go further back in the past. There will always be room for improving our understanding of natural climate variability and going back millennia in time and trying to interrogate things like sediment records and ice cores and changes in the biological world, pollen abundances, and reconstruct a picture of natural climate variability. So that work is ongoing, and there are a lot of brilliant women and men around the world who are working on those kind of things. And it does improve our understanding of natural fluctuations in climate. But the bottom line is that this picture that I showed you today is unlikely to change. We know of no individual or combined natural causes that could give you that sustained, coherent warming of the lower atmosphere and cooling of the upper atmosphere. You look at the ocean evidence, we see warming in every ocean basin. We know of no mode of natural cycles that could simultaneously warm all ocean basins. So, better understanding of natural variability, its patterns, its amplitude, great. I hope we make progress there. Is it likely to change the fundamentals that I showed you here tonight? I would say no. Yes, sir.
What do you think this has become such like a partisan issue, at least in America, or at least in the USA? Like, the sort of climate deniers that seem to almost act illogical. Like, it's almost like they have no reason to not believe it, other than they just don't. Why do you think that's such a partisan issue? It seems almost completely divided between the two political parties and what they believe in.
Great question.
Could you repeat the question, please?
Yeah, so the question is, why is this such a partisan issue here in the United States? And the gentleman who asked the question about Merchants of Doubt, I would refer you to Merchants of Doubt. It's a great book, and it provides some of the answers to your question. So, in part, ideological reasons. There are folks out there who were on the wrong side of the science on many issues, not just climate change, but on acid rain, cigarette smoking and cancer, stratospheric ozone depletion, and that was their playbook. Any science that they didn't like, that led to outcomes that they didn't like, they would cast doubt on the science and the scientists involved in the science. So this playbook has been used again and again and again. I'm encouraged, however, because I see some of those ideological barriers broken down. In Congress, for example, recently, 11 Republicans introduced a bill asking their fellow members to treat this issue seriously, saying that this is not a political issue. While one can have political differences on what to do about it, one should not view the basic science through some kind of ideological filter. So that message is starting to get through, and the message is starting to get through too that there are opportunities here, economic opportunities, that folks who figure out cheap, efficient ways of providing low carbon energy, they're going to be the leaders of the 21st century. And here in the United States, we have a choice as I see it. Do you want to be a leader or do you want to be a follower? Very, very clear choice. And to me, that signal is getting through. Okay, we haven't seen all that much evidence of that in some of the debates recently, but in the end, the rest of the world is moving on. The rest of the world has decided this is a serious problem, we're going to do something about it. And again, personal opinion here, I don't think you can adopt a cafeteria approach to international law. I want a little bit of that law here, but none of that climate stuff. I don't like that. I'm not going to eat that. And in the end, other countries are going to judge you and judge us as U.S. citizens in terms of how we respond to this global issue. So I think, the days of the deniers, the days of embracing ignorance are limited. They really are limited. The physical reality of warming is undeniable. And with every year, it's going to be much more difficult to maintain that position that nothing's happening, that this is all natural. The hope is, though, that they don't delay effective action too long. So there's this continued responsibility to do the science, to advance the science, and to talk about it, to be accountable. And again, another encouraging thing is that I know Tom has had extraordinary opportunities to talk to very influential people about the science. I have too. And some of those opportunities we wouldn't have had 20 years ago, but we're getting them now. People are willing to give you 30 or 40 minutes of their time, even if they're skeptical about this stuff, to listen, because there's some gut feeling that, okay, maybe we need to listen here. And that's encouraging to me. Yes?
More about this ocean acidity. I just recently heard about how bad it is in Monterey Bay over there now. Is it pretty widespread?
All right. Ocean acidification. Sorry, dogs.
Got the button. They're doing worse code.
I can't find the slide here, but basically, we know that from measurements at ocean stations at a number of different locations that pH has decreased. So what's happening is the ocean is drawing down some of the CO2 in the atmosphere, forming this weak acid, and that change in pH has been measured, been monitored, it's real, it's happening, and it's concerning because a number of organisms with calcareous shells at the base of the food chain are sensitive, or some of them at least are sensitive to those changes in pH of their environment, and that's deeply concerning. You don't want to monkey around with stuff at the base of the food chain. And as Tom mentioned, some of the proposed geoengineering strategies that involve solar radiation management, sort of artificial volcanoes, affect the temperature but do nothing to deal with the problem of ocean acidification. Okay, so it's a serious issue. It's gotten a lot of attention in the last few years, quite rightly so. Last chance for questions for two captive climate scientists.
Okay. Going once? Oh, yeah, there we go.
Yes, sir.
Would you want to say something about some of the effects of these various scenarios? For example, what does 800 parts per million world look like compared to 550 or 3 world?
Yeah, so the question was, so 800, 900 parts per million, what does that world actually look like? And the numbers that you see here are global means. So those temperature changes or the sea level changes are global average projections. So regionally, you get a lot of differences. You tend to get larger warming at high latitudes in the northern hemisphere. So in some regions of the globe, the warming under a business as usual scenario would be much larger than the global average numbers shown here. And that's deeply concerning. I mean, already the Arctic, as we know it, is undergoing very rapid transformation. people are sailing ships through the Northwest Passage, and there are all these concerns about how the geopolitics are going to change when the Arctic becomes a place where countries are fighting for resources and minerals. So all of this is happening in our lifetimes. What might things look like at 800 parts per million? I don't know, but everything that I've learned over my career tells me that it would be a very different world in climate terms from the world we inhabit now. And the real concern is with sea level rise. When you think of for me, when you think of the fraction of the world's population that lives at or close to sea level, and you contemplate 2-3 feet of sea level rise over the next 150 years or so, that's a different world. Florida is a different place. Louisiana is a different place. Low-lying countries, Bangladesh, small island states, it's a different world. And that's deeply, deeply concerning to me. So, again, to me, we got to address this problem now. We can't kick the can down the road. And, I remember a couple of years ago, during the fiscal crisis, politicians, banging on the table saying, it's inherently unfair to burden our kids and grandkids with fiscal debt they did nothing to incur. This is equally real, this kind of debt. And if you care about intergenerational equity, you got to care as much about the 800 parts per million world and what that kind of debt looks like as about the fiscal debt. Yes?
I've read that forestation helps planting trees, basically reversing deforestation, helps take a lot of the extra carbon dioxide out of the air. I mean, is that being seen as an option too? Is it seriously being considered? I'm just wondering.
Yeah, it's not something I'm knowledgeable about. Maybe Tom would care to weigh in there. My best understanding of afforestation, so making a dent in the problem by planting a boatload of trees, is that even if you did this in massive fashion, it wouldn't make much of a dent in the problem. Do you think that's an accurate characterization of things, Tom?
Well, one thing you can do is look at how much carbon dioxide has changed as a result just of deforestation. Okay, so we've gone from 280 to 400 parts per million, and maybe 20 parts per million of that is due to changing land use. So even if we went back to the pre-industrial world, we'd only save 20 parts per million. So, it's important to do everything we can, reforestation, afforestation, and reducing deforestation. Those things are really important. We should do everything we possibly can, because there are a lot of other implications there too. Everything is important, and there are different levels of importance, but, don't throw anything out the window.
Yes, I'll get to you next.
I want to ask, do we know how effectively the Earth can bounce back to equilibrium if we can keep, the greenhouse gas where we want it to be? Is there a way that we know how fast?
Yeah. So this question was about if we had a Harry Potter-like magic wand and could magically freeze emissions of greenhouse gases or atmospheric concentrations of greenhouse gases at present day levels, what would happen? And people have done those simulations. There's actually a lot of discussion of them in IPCC reports. They're called commitment calculations, where in model world, you wave that Harry Potter-like magic wand and you see that temperature continues to rise and sea level continues to rise because the climate system, particularly the ocean with its very long time scales that Tom mentioned, takes a long time, decades to centuries, to equilibrate to the levels of greenhouse gases we currently have in the atmosphere. So in model world, you can do that. You can increase CO2 according to how it's increased historically, and then you can freeze it and see what happens in the climate system. And the reality is that things continue to warm. Of course, not as much as if you followed a business as usual scenario. But in some of these commitment calculations, the estimated warming, if you froze things at 1990 levels, I think, of CO2, you get an additional 0.5 degree Celsius global mean warming out to 2100. And sea level continues to rise, as Tom has showed, for many, many centuries to come. Do you want to add something to that, Tom?
Yeah, that's about right. I mean, sea level's the real problem because there's a huge amount of inertia in the ice sheets and with the ocean, and sea level would continue to rise at if we freeze the concentrations of greenhouse gases at the present level, say, and of course this is totally impossible, but if we did as a thought experiment, then sea level would continue to rise at, I don't know, maybe 6 inches to 12 inches per century for thousands of years. Wow. So everybody gets washed away.
Yeah, really.
Even if we freeze the concentrations, it's really devastating on a very long time scale for ocean, near ocean communities. So that's the most serious long-term problem.
So it's a challenging problem, and those commitment calculations are really sobering because, of course, we can't do that. We don't have that Harry Potter-like magic wand, not yet. Yes, sir.
Okay, I've been encouraged by changes in attitudes about taking this whole issue much more seriously, and especially among young people. But I think it's safe to say that there's going to be some controversy continuing into the future. And I was just wondering if you had any advice for young scientists who choose to go into a field like this or any controversial field. I mean, one obvious thing is watching, you say, email and write newspapers sometimes. But things, what would help a young scientist who's thinking of going into something where they might face attacks from, say, people with vested interests?
Yeah, great question. And I was kind of concerned after the incident you mentioned, ClimateGate, and the unauthorized release of many emails from the Climatic Research Unit at the University of East Anglia and all the mischief that was done with that. I was concerned that would deter young scientists from getting involved, that it would say, hey, wow, this is something where there's a heck of a lot of scrutiny, and maybe I don't want that. In fact, what I sensed was exactly the opposite. That people came to me and said, how can I get involved with the IPCC? How can I get involved with this kind of research? How can I do a PhD in this area? Folks want to make a difference in the world. I talk to students around the country, around the world, and that's pretty much the message I get in most places. People are not deterred by those kind of things. They want to make a difference in the world. They understand that, this is their world, and we're kind of screwing it up. We've not done a particularly good job with stewardship, and it's up to them. And they want to say in that, quite rightly so. So I don't sense a sort of deterrence factor. Answering the other part of your question, there are all kinds of resources now out there to teach you to be better communicators. Resources that were not available 20, 25 years ago. So there are things like the Climate Reality Project, Union of Concerned Scientists. There are Leopold Fellows. There are all sorts of mechanisms for learning how to be a better communicator about the science. And some of these programs also put you in situations where you're tested. You're put under adversarial conditions. You mimic congressional testimony, and you learn how to do it better. Those things were unavailable, and it's terrific. I see every day young scientists who are brilliant communicators, much better than I could ever aspire to be. And that is deeply encouraging to me.
I got one last one.
Go for it.
Yeah, that word, even though we know it's global warming, right? That word of saying global warming, you have people say all the time, well, I don't feel it any warmer, right? It's not any warmer to me, right? I prefer the word climate change, I mean, was that a big problem when we started off saying global warming, using that terminology?
A great question, and I've actually been asked that question in congressional testimony. What's the difference? What's the distinction
Right, exactly,
between
yeah.
global warming and climate change? And was it just Frank Luntz who, influenced that transition? Again, here's my highly personal take on that. Global warming conveys an expectation. It sort of conveys the expectation that every place on the planet is going to warm, and every year is going to be inexorably warmer than the previous year. There are people who interpret global warming that way. And of course, that never was our scientific expectation, that every year was going to be a little bit warmer than the previous year, every place on the Earth was going to warm.
Right.
Signal and noise, man. Signal and noise.
Right.
I mean, we know that there is noise in the system. There's rich variability on year to year, decade to decade, century to century time scales. That has complex patterns. These individual modes interact with each other. So we know that there are going to be locations over short, noisy periods of time where you get cooling. We know that, if you get a big El Nino in 97, 98,
Yeah.
then if you look at changes over a short period of time, you can get a short-term cooling trend. We see that in simulations and in observations. It doesn't invalidate our understanding of the gradual warming signal we expect to emerge from the noise of natural variability due to slow human-caused changes in levels of heat-trapping greenhouse gases. So that's the challenge. Again, it's sort of a communication challenge.
Right, it's a
to tell
communication
people
challenge.
that there's
Absolutely.
signal and noise here in
right.
model world, in the real world, and short-term cooling, one cool winter, does not invalidate this understanding. It's expected. So to me, climate change is a sort of more accurate representation of our expectations than global warming.
I agree, because we have seen dramatic climate changes across the world. Hurricanes when they're not having them, and people realize that they actually can understand that, see that.
But the thing to note in the same breath is that we expect warming. We continue to increase heat-trapping greenhouse gases. The planet's going to warm. Surface is going to warm. Lower atmosphere is going to warm. That's our expectation. But there's still going to be noise in the system. There always will be. There was before humans were on the planet. There's going to be noise in the climate system far, far into the future. That's the way it is. So all of this stuff is about how do you identify that signal that's embedded in this rich noise of variability. And you got to tell people there's both. It's not pure signal, it's not pure noise, it's both.